Hello and welcome to another episode of Slam TV. I'm Professor Roger Yang, and today we're going to learn about the student T distribution. Luckily for you folks at home, we've got a very special guest for you. Nothing about him is normally distributed. He's a student of stats and a student of life. He's Professor Jay Cho.
Thank you.
Hey Jay, how's it going?
Pretty good, not bad. Oh, by the way, do you have a phone charger on you?
Why? What percentage are you at?
Ooh, I'm at 15%. If it drops below that, I get a little bit anxious.
Oh really? I wonder what my phone is at.
Oh, what's wrong? Are you okay?
My phone's at 20%. I tend to get a little bit nervous and anxious when my phone drops below 20%.
Huh. Yeah, that's true. My students, they get anxious and they try to charge their phone during class all the time.
I wonder what the average battery percentage is where a student starts to feel anxious and needs to charge their phone.
If only there's a way we can use statistical techniques to figure this out. Oh, you text me. Now I'm at 14%. Thanks. Confidence interval, of course. Why didn't I think of that?
It must have been your phone anxiety. Hey Jay, why don't you lead us through the construction of the confidence interval for this particular example?
Okay, first of all, do you think we're dealing with confidence interval about a mean or a proportion?
Well, this is about battery percentage, right? Every other time we've seen percentage, it was about proportion.
Right. Unfortunately, in this case, the percentage does not indicate that we have a proportion here.
Why is that?
Because we are actually measuring the amount of battery left, right?
Oh, I see. You're saying this is quantitative data because we're measuring the amount of something, not categorical data.
Right. For categorical data, if it was categorical data, we'll ask, is your battery charged or not charged? But now we're not dealing with that.
Ah, I see. In this case, our survey question will be, on average, how much battery percentage makes you nervous?
Right, so...
or anxious?
Exactly. So we are basically trying to say, on average, what percentage makes people anxious.
This seems like it's a confidence interval about the mean. Didn't we already just look at an episode in the confidence interval about the mean? Remember we were talking about your mean coffee consumption? So you're saying that if I create an interval that has a $10 range, and if your mean coffee expenditure is within that interval, then I win $100?
Exactly, and if it's outside of interval, then I win $100.
Good times.
Okay, let's try to figure it out. Let's go gather some sample data.
Collecting sample data is exhausting.
I know, exhausting, right?
Hey Jay, why don't you lead us through the construction of this confidence interval for the mean?
Okay, first of all, what confidence level do you want to use?
Let's use the standard 95% confidence.
Okay, and then we need a point estimate. What's the best point estimate for this case?
Well, since we're estimating the population mean, the best point estimate for the confidence interval of a population mean would be sample mean x bar.
Okay, sample mean, great. Can we go over the sample statistic from our survey?
Sure. Let's see what our survey says. Well, it says our sample mean x bar was 25.9.
Okay.
We had a sample size of 41, and we had a sample standard deviation of 20.8.
Okay, great. We got that. Now we need the margin of error. Do you remember what we did for margin of error last time?
Yeah, we used the margin of error formula, right?
Okay.
Well, in our margin of error formula, we first see we have the critical value z alpha over 2. Z alpha over 2 comes from the normal distribution corresponding with 95% confidence, and that's going to be 1.96. Next, we have our sample size, and our sample size is 41, so that goes in the denominator. Oh wait, what's our population standard deviation sigma though?
Well, we have our sample standard deviation S, but we don't know the population standard deviation sigma.
How did we get it last time?
Did you call your X hacker Heidi?
Oh, you mean x, like an unspecified, unknown random variable? She knows me,
Yeah?
but I think calling her is a great idea.
Calling old flame.
Hey Heidi, how you doing?
Oh dear.
Dear, see, she likes you.
Hey, Heidi, we need your help.
Yeah, we need your math hacking skills.
We need to know the population standard deviation of the battery percentage that makes students anxious and need to charge their phone.
Sorry, can't help you.
Can't or won't?
Well, despite leaning slightly closer to won't, I literally cannot help you with this.
But Heidi, you helped us find the population standard deviation last time when we wanted to know Jay's mean coffee expenditure.
That was different because the population was just all of Jay's coffee consumption. All of that data was stored on his fancy coffee app. Here, our population is all the students that have cell phones. I can hack into a computer system, but I can't read people's minds. Except maybe for Senor Simpleton over there.
Hey Heidi, try reading my mind.
OMG, I'm getting a clear message.
You did?
It said, goodbye.
Man, no population standard deviation sigma.
I know.
We're totally screwed.
Don't worry, Roger, we're not totally screwed.
We're not?
Right. Not knowing population standard deviation sigma is a pretty common problem.
Oh, how do you overcome this problem?
We're just gonna have to use different distribution.
A different distribution? A distribution that's not normal? Does Norm know?
Yeah, Norm knows it pretty well. Actually, it's his grad student, student T.
Wait, Norm is a professor with grad students?
Apparently, let's call him.
Okay.
Calling boring norm.
Hey guys, what's up? Oh, Jay, do you still have my tape measure?
No.
Hey Norm, we heard that when you don't know the population standard deviation, you can't use the normal distribution. We were wondering if you could help us handle this situation.
That's right. That's why I've been training my star student to follow in my footsteps and handle these cases where sigma is unknown.
What's your student's name?
We call him Student T. In fact, he's in my office right now. Would you like to meet him?
Yes,
Yeah.
please.
I'll leave you guys in the capable hands of my top grad student, Student T.
Hello, student T. Can you tell us a little bit more about yourself, please?
Hey, I've got certain similarities to Norm. He's bell-shaped and symmetric, and I'm bell-shaped and symmetric.
Oh yeah, you guys are both bell-shaped and symmetric. You guys do look pretty similar.
I'm a little shorter and wider than Norm, the normal distribution.
Because you're a little shorter, you gotta be a little wider than Norm, huh?
Norm typically asks us for two important numbers, mean and standard deviation.
Yeah. What are the numbers that are important to you, student T?
There's really only one important number. That number is degrees of freedom.
And how do you calculate that?
Degrees of freedom is just n minus 1.
Oh, it's just the sample size minus 1. So with a student T distribution is shorter and wider than the normal distribution.
Okay.
And in the normal distribution, you have two important numbers, the mean and standard deviation.
Right.
With the student T distribution, you just have one, which is the degrees of freedom.
Okay.
Are there any other differences that you have, student T?
There's just a couple more.
What are they?
Another thing that's interesting is that different degrees of freedom give different curves. All right, let me show you. This is what it looks like when the degrees of freedom are 5. And this is what it looks like when the degrees of freedom are 10. This is what it looks like when the degrees of freedom are 15.
I see. So we can determine which curve we have by looking at the degrees of freedom?
That's right, Roger. And this is the distribution we use when we're working with a mean and we don't know what the population standard deviation sigma is. We modify our original margin of error formula.
Okay, cool. Let's look at our margin of error formula again. So our margin of error formula says z alpha over 2, which is the critical value, times sigma divided by the square root of n.
And we need to modify something. Since we don't know the population standard deviation sigma, we need to use the sample standard deviation S.
Is that a good idea? I thought sample standard deviation was a poor estimate of population standard deviation.
It is. It has tendency to underestimate the population standard deviation sigma.
Oh well, I mean, we don't know sigma, so we're forced to use S instead anyways.
Yeah, I guess.
Now you guys are talking about my specialty. Since the graph is short and wider, the critical value T alpha over 2 will be further out from the center.
Can you use an example to show us this?
Sure. Let's say our sample size is 41. Since the degrees of freedom is the sample size minus 1, our degrees of freedom in this case will be 41 minus 1, which is 40. In order to find the critical value T alpha over 2, we need the area to the left. To find the area to the left of T alpha over 2, we add the area in the left tail of 0.025 plus the area in the middle of 0.95 to get a total area of 0.975. When we put these values in our calculator, we get a T alpha over 2 of 2.021, which is bigger than our Z alpha over 2 of 1.96.
Oh, I see how the critical values are further out from the center on the student T distribution. I mean, the critical value is larger.
And this countered the fact that sample standard deviation S underestimates the population standard deviation sigma.
Wow, that's genius.
All thanks to student T.
Hey, student T, can you tell us exactly how you found that critical value T alpha over 2?
I use the inv_t calculator function. You simply enter the area to the left of the critical value and the degrees of freedom. For 95% confidence, the area to the left of the critical value is 0.975, and our degrees of freedom for a sample size of 41 is 41 minus 1, which is 40.
Awesome. That's exactly what we're looking for.
Thank you, student T.
Thank you. Now let's take a look at our new margin of error formula. So our new margin of error formula for mean when sigma is unknown is T alpha over 2 times S over square root of n.
So let's calculate the margin of error formula for our battery percentage example.
So the T alpha over 2 we got was 2.021.
The sample standard deviation S was 20.8.
And the sample size n was 41.
We enter all these values into the margin of error formula and we get
The margin of error E of 6.57. So what do we do with this margin of error E?
well, we take the margin of error E and we add and subtract it to our point estimate x bar in order to get the endpoints of our confidence interval.
Yeah, let's calculate this.
Our point estimate, which is x bar 25.9, and subtract the margin of error E, which is 6.57, and we get a left endpoint of 19.33.
And to get the right endpoint, we get 25.9 plus 6.57, so you get the right endpoint of 32.47.
So our total confidence interval for the mean is 19.33 and 32.47.
Wow, it sounds like I'm below the mean.
Why is that?
Well, because we are 95% confident that on average, students feel anxious when their battery life is between 19.33 and 32.47. Mine is 15%, so that's less than the left endpoint of the confidence interval.
Oh, you're saying the entire confidence interval is completely above your value of 15%.
That's why I'm below the average. How about you, Roger?
Well, 20% battery percentage makes me nervous, which is still in the interval, so I guess that might mean I'm pretty average.
Well, you're just not as relaxed as me, I guess.
I mean, look at you. You're so relaxed.
Tell you what though, there's one thing that makes me anxious.
What's that?
Can't seem to find Norm's tape measure. Normally, he's not that angry, but I gotta get back his measuring tape back to him.
Otherwise, he's going to be enormously angry.